The human metabolic engine runs on an evolutionary operating system optimized for resource scarcity. For over 200,000 years, this biological hardware prioritized energy storage, relying on complex feedback loops to preserve glycogen and lipids for rare windows of caloric abundance. Today, that ancient hardware faces a system-wide software glitch. The modern environment delivers a continuous, unregulated deluge of high-velocity, ultra-processed food inputs. These refined carbohydrates and added sugars consistently overload the processing capacity of our metabolic hardware. Legacy healthcare systems often misdiagnose this architectural mismatch. They rely on a reactionary, pharmaceutical-first model. This approach treats downstream symptoms while ignoring the corrupted upstream inputs that drive cellular degradation. We are going to conduct a forensic autopsy on this systemic hijack, tracing how these inputs route toxic data through the liver, the brain, and individual cells. The chronic disease epidemic follows a predictable pattern, a biological computing architecture crashing under the weight of inputs it was never designed to process. To bridge the gap between abstract metrics and clinical reality, Dr. David Unwin developed an educational framework that replaces the standard glycemic index. This framework uses a teaspoon of sugar equivalent. Exactly 4 grams of pure carbohydrate represent 1 teaspoon. A healthy adult maintains a circulating blood glucose concentration of exactly 1 teaspoon. This 4-gram limit is tightly regulated across the body's 5-liter blood volume to maintain homeostasis. Standard starch-heavy meals introduce a high-velocity carbohydrate load that dwarfs this physiological baseline. These inputs mathematically exceed the blood volume's hard-coded processing limits. To manage this surplus, the body executes massive insulin surges to clear the glucose from the blood as quickly as possible. Systemic cellular overload begins the moment dietary inputs surpass these regulatory thresholds. While glucose is processed by cells throughout the body, fructose absorption follows a distinct and inherently pathogenic metabolic routing. Fructose absorption entirely bypasses peripheral circulation. It is funneled directly to the liver via the portal vein. Inside the hepatocytes, fructose escapes the critical regulatory checkpoint of glycolysis by bypassing the PFK1 gatekeeper enzyme. This results in an unregulated substrate flux that proceeds without any feedback inhibition. This creates a surplus of acetyl-CoA, forcing the liver into de novo lipogenesis, the rapid synthesis of saturated fatty acids. The resulting intracellular malonyl-CoA acts as a direct inhibitor of CPT1, which completely blocks the liver's ability to burn fat for energy. Because fat oxidation is blocked, the liver must accumulate these newly synthesized lipids, leading to steatosis. Standard blood panels for AST and ALT often fail to catch this damage due to extreme diagnostic latency. Clinical reference ranges for these enzymes are based on populations already compromised by metabolic syndrome, allowing early-stage fatty liver disease to go undetected. The liver essentially acts as a silent data sink, accumulating lipid deposits for years before legacy medical systems register an alarm. Persistent consumption of these metabolic substrates stems from an engineered neurochemical hijack. Hyper-palatable ultra-processed foods trigger intense dopaminergic surges directly inside the brain's nucleus accumbens. PET scans demonstrate that these engineered inputs stimulate the exact reward circuits involved in cocaine addiction. The brain defends itself against these surges by physically down-regulating postsynaptic dopamine D2 receptors. In stages 1 and 2, anticipatory dopamine spikes lead to neuroinflammation and mild tolerance, where individuals begin overeating during periods of stress. By stages 3 and 4, reward deficits and compulsive food-seeking behavior weaken the connections to the prefrontal cortex, compromising impulse control. In stage 5, chronic D2 downregulation induces leptin resistance. The brain becomes blind to the body's fat stores and interprets the signal as starvation. This neuroadaptive remodeling creates a chronic hedonic deficit, locking the individual into a compulsive loop of tolerance and dependency. Before we explore how this metabolic dysregulation directly fuels cellular oncogenesis, this systems analysis is brought to you by DJAMGAMIND. To dive deeper into advanced analytical frameworks and cognitive optimization, subscribe to DJAMGAMIND on Apple Podcasts or visit jamgammamind.com for more. Metabolic dysregulation directly influences the initiation and progression of cellular malignancies. In the 1920s, Otto Warburg discovered a distinct metabolic phenotype in tumor cells. This Warburg effect describes how cancer cells bypass normal mitochondria, converting glucose into lactate even when oxygen is abundant. To compensate for this massive energy inefficiency, cancer cells upregulate their glucose consumption by a factor of 10 to 100. Chronic systemic hyperinsulinemia continuously activates a PI3K-AKT signaling cascade, which drives this metabolic shift. During the first phase, AKT inactivates TXNIP, which locks GLUT1 transporters onto the cell membrane to facilitate an unregulated influx of glucose. In the second phase, ACT activates PFK2, bypassing energy checks and forcing the glycolytic pathway to run at maximum velocity. Diets high in refined starches create an environment that provides cancer cells with both the growth signal and physical fuel required to metastasize. We have mapped how engineered inputs bypass homeostatic limits, trigger hepatic lipid accumulation, structurally hijack dopamine receptors, and physically fuel oncogenesis. This is more than a health crisis. It is an algorithmic arms race where the human metabolism is caught in the crossfire. Food conglomerates now deploy sophisticated machine learning algorithms specifically designed to engineer highly addictive, hyper-palatable foods. These algorithms mathematically optimize flavor and texture to maximize the unnatural dopaminergic spikes we've analyzed. On the defensive front, health technology platforms are utilizing predictive artificial intelligence to detect metabolic dysfunction before clinical markers alarm. Machine learning algorithms analyze glucose response curves from continuous glucose monitors to predict early-stage beta cell dysfunction. These support vector machine algorithms predict fatty liver disease using routine biochemical metrics, bypassing the lag of traditional liver panels. To reverse the modern chronic disease engine, we must move past reactionary symptom management, correct the corrupted upstream inputs, and begin patching the human metabolic software.